Yeah,
Right?
it's visible, right? Okay.
Yeah, perfectly all right. I can see your mouse also. Cursor is moving fine.
Oh, okay.
Yeah, good. Maybe we will wait for a few minutes because people will
Yes,
join.
sure. Yeah.
Okay, so I will let you know when to start.
Mhm.
Okay, so I think we can start because we are already 3 minutes past the scheduled start.
Yes. Okay.
Yeah, so hello everyone. Thank you for joining. Today we have Dr. Eswaraiah Chakali as a seminar speaker. So for many of us, he is not a known person. He has done PhD from Aries only in 2014, and after PhD, he was a fast fellow at NAOC in China for around 3 years, and then even before he did 5 years of postdoctoral research at NCU and NTHU of Taiwan. Currently, he is a Ramanujan Fellow at the Indian Institute of Science Education and Research in Tirupati. His research interest includes the importance of magnetic field in star formation processes and study of the dust grain properties at various galactic environments by using multi-wavelength dust polarimetry. So welcome, Dr. Chakali. We are happy to have you here. You can start now, and around 40 minutes from now, I will send you a reminder for remaining 5 minutes.
Yeah.
So you may please start now. Okay.
Thank you, Vaidehi, for brief introduction, and thank you for this opportunity to speak with you all. So I think it gives me an immense pleasure to talk to all his faculties and everyone. Yeah, it's a kind of after a long time giving a talk in front of the Eric's colleagues. So I'll be presenting today on the importance of magnetic fields based on the multi-wavelength polarimetric observations. So in this talk, I'll be mainly talking about the interplay among the various key parameters, magnetic fields, turbulence and gravity and stellar feedback. So these are the important key parameters which can play an important role in the formation of multiple clouds and subsequently their collapse and star formation in the dense cores. So I start with this interesting figure showing the overall picture of the general interstellar medium. You can see that this is the color composite image made based on the multi-wavelength observations, and you can see that these are the dark patches. These are mainly the cold and dense regions where the star formation can actually happen. So as a definition, the space between stars is not completely empty, but rather filled with tenuous gas and dust grains. So even though dust grains occupies only 1% of the 1% of the total interstellar medium, but it can play an important role in the star formation process. So generally, the interstellar medium can actually appear as a clumpy or patchy. So because of the total extinction of the stellar photons from the stellar background stars, you can see that the molecular clouds appear like a silhouette or dark patches against the bright background of the sky. So generally, the interstellar medium is so much inhomogeneous, and whose temperatures ranges from 10 Kelvin to 10 to the power of 4 Kelvin, and the densities also ranges from 100 to 10 to the power of 8 particles per centimeter cube. So, and this interstellar medium can be found in different phases: molecular to neutral, atomic, and ionized forms. So, I'll be talking about the cold and dense molecular clouds. So since the star formation actually happens in the dense patches, so I'll be showing the importance of multi-wavelength observations here. So in this slide, so essentially show the importance of multi-wavelength observations, because when we observe a small cloud in the optical region, our observations will be confined to the low density regions, and because of the heavier extinction in the lower wavelengths, we cannot see anything inside the molecular clouds. And when we look at the same cloud in the near infrared wavelengths, because of the relatively less extinction, the higher wavelength radiation can penetrate through the molecular clouds, and we can probe the physical conditions inside the molecular clouds. So as you can see in the middle panel, because of the because the lower radiation, the higher energy radiation, or the bluer part of the electromagnetic spectrum can be easily get absorbed or scattered by the intervening interstellar medium, intervening interstellar dust. And since the higher wavelength or the near infrared wavelength can go through the interstellar medium, we can actually probe the relatively denser regions. However, if we want to trace the even more denser regions, we need to observe in the submillimeter wavelengths to probe the dust emission. Okay, so the right panel actually shows the variation of interstellar extinction as the inverse function of wavelength. You can see in the ultraviolet for ultraviolet, the extinction is higher in comparison to the extinction at near infrared wavelengths. And if we can defect the structure of molecular cloud in the kind of lake structure, you can see that in the optical and near infrared wavelengths, we can essentially trace the physical conditions in the outer regions of the cloud. But if we want to trace even more deeper regions or inside the dense cores, which are actually forms at the center of the clouds, we need to go towards the submillimeter wavelengths or radio wavelengths. So if we can have the multi-wavelength observations, we can actually trace the physical conditions from the higher, larger scales and low density medium to the smaller scales and high density regions. And similarly, if we can assume assume this cloud as a gravitational potential, and if you can see mass distribution, most of the mass will be concentrated in the denser parts or deeper inside the clouds. And if we have only the gravity and there are no other forces, because of the gravity, the dominance of gravity, all the material should go towards the center of the cloud and collapse and form stars. Okay, if this is the situation, if only the gravity is only the sole factor is acting in the clouds, then there should be a high star formation rate should be observed, and all the molecular cloud should end within few less than 1 million, if you say. Okay, so if there is no other forces like opposing forces, I'll come to the what are all the opposing forces in the next slide. If only the gravity is the sole factor, then all the clouds should be collapsing and form stars in a high efficient way. But if we look at the general properties of the molecular clouds, the masses ranges from 100 to 10 to the power of 7 solar mass, and sizes are ranges from 1 to 100 parsec, and then mass density. If we can calculate, if you can just convert these gas densities from 10 to the 3 to 10 to the 5 centimeter cube into mass densities. So the values will actually ranges from 10 to the minus 21 to 10 to the minus 9 gram per centimeter cube. So if we can substitute this gravity, this mass density, and this is the gravitational constant, and we can estimate the free fall time scale. And so by substituting all these parameters, we can get the free fall time scale as 0.1 to 1 million year. So if only the gravity could be the factor, then the star formation should actually end up within less than or equal to 1 million year. But if we look at the lifetime of the molecular clouds, they are very high, of the order of 10 million year. So that means that so there are several factors which can be opposing the gravity, and then those factors are actually prolonging the lifetime of the molecular cloud. So if there are no other factors, then all the molecular clouds, the lifetime should be of the order of 1 million year. But the observations indicates that the lifetime of the molecular clouds is very high. So some factors coming into play, and then they are actually stopping the cloud from gravitational collapse. So what I want to conclude in this slide is that so there could be important factors. They might be preventing the clouds from gravitational collapse within a free fall time scale. Or in other words, those factors can be prolonging the lifetime of the molecular clouds. And so what recent observations are indicating that based on the Herschel observations, it has been shown that most of the molecular clouds are found to be in a kind of filamentary like structures. You can see that there are low density filaments and then high density filaments. And then if you see the top right panel also, these dark patches are nothing but the elongated filamentary molecular clouds. You can see that they are kind of elongated. And if you see the magnetic field orientation, as shown with the black segments or yellow segments. In some of the clouds, they are perpendicular to the elongated molecular clouds or the elongated filamentary-like structures. In some of the clouds, they are parallel to the large scale, long scale or the major axis of the filamentary cloud. So there are two scenarios actually. And if you look at the distribution of the dense cores as shown in the bottom panel, the the red dots are indicating the dense cores. You can see that these are distributed in a chain-like fashion along the major axis of the filament. So there is an intriguing connection between the large scale filamentary molecular clouds and the dense cores and the subsequent star formation. So based on these observations, it has been proposed that there are the star formation involves two-step process. In the first step, turbulence and magnetic fields actually collaborate with each other, and then they form the intricate network of the filamentary molecular clouds. So the turbulence, if you see the large scale turbulence, is a kind of, it looks like a supersonic velocity or expanding ionizing from the blast from the supernova explosion. So if you have something like a large scale flows that actually sweep up the interstellar medium, and then eventually they can form the elongated filamentary molecular clouds in the larger scale. So that scenario is something like sweeping on the ground. So if we sweep the ground, and then at the end we can see the accumulation of dust, right? So the process is similar to like that. And then whereas the magnetic fields can actually channelize the material, because there is a higher considerable amount of ionization in the low density interstellar medium, and these ions can couple with the magnetic fields. So there is a very good flux freezing condition prevails in the low density medium. So and because of that, the matter can actually flow along the magnetic field lines in a better way. So the turbulence can actually can throw the can accumulate the material, but the magnetic fields can channelize the materials. So these two factors can collaborate with each other and then form the elongated filamentary molecular clouds. And once these dense structures formed in the filamentary structure, these filaments can fragment further and then collapse to form the stars under gravity. So this gravity can come into picture in the later stages whenever there is a threshold, the density greater than the threshold density. And if you look at the properties of the magnetic fields and turbulence, they are not constant across the scales and densities. If you look at this top panel, this is essentially the magnetic field strength versus densities. So you can see the in the large scales or the low density regions, the magnetic field strength is low, around 10 microgauss. And here, what is proposed that the magnetic fields can channelize the low density material. So this is what it has been proposed. In such a scenario, the low density striations or the gas motions can align along the magnetic field lines. Beyond certain threshold density, something like greater than 10 to the power of 3 hydrogen atoms per centimeter cube, you can see the role of magnetic fields can change. So here the magnetic fields can aid the material flows and form the filamentary-like structures. And beyond certain threshold density, the magnetic fields can oppose the gravitational collapse. So whenever the gravity pulls the magnetic field lines, the magnetic field strength can increases. So there is a beyond certain threshold density, you can see that there is a power law relation. The index is something like 2 to 2/3. So in this diagram, we can say that the role of magnetic fields can be different in the low density regions in comparison to the high density regions. In the low density regions, magnetic fields essentially can help the material flows. And in the high density regions, the magnetic fields can oppose the gravitational collapse. And if you look at the energy spectrum or the variation of the level of turbulence as a function of length scales, as shown in the bottom panel, you can see that it actually follows something like a power law function. So in the low density regions, in the right part of the figure, you can see that the turbulence is supersonic. And if you convert into kilometers per second, that will be higher than something like a few kilometers per second. And if you look at the level of turbulence at the low density regions, it will be subsonic turbulence. So when we go and look at the turbulence in the dense cores, that turbulence can be dissipated. So However, the turbulence is actually intermittent phenomena. Turbulence can be, it can dissipate very easily. It's something like a turbulence or disturbance in human beings. So the turbulence can happen in a, kind of certain period, but it cannot prevail for a longer time. So turbulence can be dissipated. So it can actually vanish. But the observations show that the turbulence actually prevails at across the various scales. So how the turbulence can be generated. So this is the mechanism. So the protostellar jets and outflows are the winds and UV radiation from the OB-type stars, or the expanding ionizing fronts from the H2 regions or supernova explosions can actually replenish the interstellar medium with the continuous turbulence. So these are the important factors and their parameters here. And as I think I explained earlier, so this gravity, turbulence, and magnetic fields can actually collaborate with each other. So earlier I mentioned only the turbulence and magnetic fields, and also here actually we are adding the gravity, and these three factors can collaborate with each other and then finally drives this star formation process. So here you can see that this is a very intriguing picture. If we look at the interaction between turbulence and magnetic fields, they interact with each other, and then they have different roles actually. For example, if the magnetic fields are stronger and turbulence is subsonic, and then the subsonic turbulence can actually go along the magnetic field lines. So in other words, magnetic fields can actually channelize the subsonic turbulent flows, and it can result in a very important result here, as shown here. So if the magnetic field is stronger and the turbulence is subsonic, and you can see there is a parallel configuration between the filaments and the magnetic field lines. And if the turbulence is very stronger, that can actually compress the magnetic field lines, and the magnetic field strength can be increased. So similarly, magnetic fields and the gravity can I think they interact with each other. And the low density medium, magnetic fields can drive the gravitational force. In the high density medium, the magnetic fields can stabilize the cloud against the gravity. And similarly, the gravity and turbulence can also interact with each other. Okay, if we have a turbulence, there will be a, there won't be the gravitational collapse. And so in the other words, turbulence can actually stop the gravitational collapse. And in the other scenario, the gravitational flows towards the denser regions can also generate the turbulence. So they interact with each other factor, and then they drive the various physical processes. In the right panel is also very important in a way that if you have only the gravity as shown with the red curve, the star formation rate should be very high. Like if we have 100 solar mass cloud, and that cloud should form into 100 stars, each star with one solar mass, but that is not actually has been observed. And then if we introduce the turbulence and then gravity, you can see that the lifetime of the molecular cloud has been reduced, and the star formation rate is also has been reduced. And similarly, if we can incorporate gravity, turbulence, and magnetic fields and stellar feedback, you can see that all these factors can reduce the star formation rate to few percentage, like 3 to 5%. And also the lifetime of the molecular cloud, as shown in the top scale, that can actually increase it from 1 million year to 7 million years. So introduced by having all these factors, we can actually have the reduced star formation rate that would actually match with the observations. And also these three factors can prolong the lifetime of the molecular clouds. So what observations actually infer? So observations actually infer from a low resolution Planck space instrument. We can see that the magnetic field orientation as shown with the drapery patterns, the background color scale is corresponding to the current density. So in the adjoint view, you can see that magnetic field in the galactic plane is almost parallel to the galactic plane. But in the higher galactic latitudes, it follows simply the higher kind of ionized loops. And if you look at the magnetic field orientation within the nearby molecular clouds, in the Taurus region, you can see in the large scale magnetic field as shown with the drapery patterns, as well as the black vectors from the stellar polarimetry in optical and infrared wavelengths. Magnetic field orientation is preferably perpendicular to the elongation of the filament. And this picture is also seen in the pipe nebula. You can see that this is the elongation of the filament. This is the filament, and the magnetic field orientation is like that, perpendicular to the large scale filament. And this picture is generally been observed in the low density regions. So so these observations indicates that Since there is a preferential orientation between the magnetic fields and then clouds, they are actually exhibiting a perpendicular configuration. These magnetic fields play an important role in the accumulation of matter. And these observations are actually confined to the low density regions, like Planck, because the Planck has very higher beam, like 5 arc minute size. So we cannot trace the magnetic fields in the denser regions. So one of the important question is that whether these magnetic fields which are ordered, which are uniform in the large scale magnetic fields, whether these magnetic fields can be preserved and they exhibit the same configuration within the dense cores. So this is the problem. So we do not know whether these magnetic fields are preserved across various scales and densities. But according to the simulations with stronger magnetic fields, it has been shown that magnetic fields are preserved and they are organized from larger scale to smaller scales. So this is in the cloud scale. You can see the scale like 5 parsecs, and the core scale is something like 0.2 parsecs. Still, the magnetic fields are preserved. And then, if you look at the vicinity of the protostars, it actually preserved the large scale magnetic fields. And because of the ambipolar diffusion process, these magnetic fields actually attain a hourglass shape like structure, which has been observed based on the submillimeter dust observations. And so if this is the true, if magnetic fields are preserved across the scales, and they should preserve their orientation, and they play an important role across the various scales. But recent observations have shown that this is not the case. Okay, so if in one of the results, the larger scale magnetic fields are actually threading perpendicular to the elongation of the filament, as shown in the top left panel. But if we have the gravity-driven gas motions along the one of the filament, this perpendicular configuration can actually switch into parallel configuration. You can see here. Okay, so if this is the case when we have the gravity-driven inflows. So here the magnetic fields are actually not preserved. So something is happening at the smaller scale. And then similarly, if we have the H2 compression, if you have the kind of expanding ionizing fronts, and then they're interacting with the dense cores. So at the interaction region, you can see that magnetic fields can attain a something like a twisted like structure or the bow like structure. And then if we look at the magnetic fields at the smaller scales, and then and in case of dominance of the protostellar outflows, so magnetic fields can exhibit a complex orientation or complex morphology. And also in the region where the turbulences may be dominating and magnetic fields are weaker, then also we cannot see the order magnetic field orientation. So this is the case wherever we have something like a gravity is dominating, and or the H2 region actually compressing the magnetic fields, or protostellar outflows are dominating, or turbulence can be changing the magnetic field orientation. But in order to understand the the original magnetic field role, we need to probe the magnetic fields in a quiescent region. And so Taurus or the LDN 149 can be such ideal laboratory. So this image is actually showing the the column density map, the background image. You can see the elongated filamentary like structure. So the color scale is corresponding to the column densities, and this is where the higher column density and where some of this filament is actually being fragmented into several dense cores. And if we look at the magnetic field orientation at the large scale, as inferred by the segments with the different colors. So this yellow is from the Planck, low resolution dust polarimetry, and cyan, and then this orange color or violet color. These are from the near infrared and optical polarimetry respectively. So you can see that none of these observations can trace the magnetic field orientation in the dense cores. And you can see the large scale magnetic field orientation is very uniform and essentially threading perpendicular to the magnetic field orientation. This is essentially matched with the existing observations. We do not know what is happening at the dense cores. So in this study, we have conducted sensitive dust polarization observations towards B213. This is a small portion is B213. This is part of the large scale molecular cloud called Taurus. So we have used JCMT telescope, and which has the very sensitive camera SCUBA2 core, SCUBA2, and then polarimetry called POL2. And these observations have been acquired as a part of, a large program called Bistro. Bistro stands for B fields in star forming region observations. So this is a large program aimed to perform the high resolution observations towards the dense cores in the Gould belt molecular clouds. So this is the JCMT 14-meter, 15-meter telescope, and these are the various telescopes on top of the Mauna Kea. So this Bistro program is a large program which involves the various countries, not only East Asian countries, but also UK and Ireland, Canada, and also recently Thailand and Vietnam also become observers as a part of Bistro. And this contains like 150 collaborators, and this program has been very productive, and it is actually evolving into various generations of the Bistro program: Bistro 1, Bistro 2, and Bistro 3. And so this is the observing results in this one, as these white contour essentially shows the column density contour at 10 to the power 22 per centimeter square, and the black contours are the dust continuum emission at 13 millijansky per beam. So this is from our observation. The background image is from the JCMT Stokes eye, or the dust continuum image. You can see that this filament has been clearly fragmented and then fragmented into several cores, and some of the cores are actually forming stars, this central one and the bottom left one, and the rest of the cores are actually not forming stars. And one core is actually more evolved core, which is actually the class 3 source, hosting the class 3 source. And you can see that in 3 of the cores, we can detect only one segment, B field segment, as shown with the red vectors. And rest of the cores, there are kind of significantly large number of B field segments. And you can see that in the previous diagram, I show here that the large scale magnetic field orientation is very ordered, and which is going from top left to bottom right corner. But you can see that the same configuration has been retained in one core, but not in the other cores. So when I estimate the weighted mean B field orientation as shown with the red segment, and then I just want to compare this small scale B field in the cores with the large scale magnetic field orientation from the Planck polarimetry as shown with the yellow segments. You can see that in one core, only the small scale B field orientation is well preserved, and which is parallel to the large scale. And you can see that the outflow orientation is also aligned with the large scale magnetic field orientation. But the magnetic field orientation in the 2 other cores is completely decoupled. They are actually, shifted from kind of 90-degree orientation to something like 0-degree orientation. So you can see that even though these 3 cores are formed from the same parental molecular cloud, and this parental molecular cloud having the uniform magnetic field orientation, but the magnetic field orientation at the smaller scales is drastically different. Except in one core. And this is all about the magnetic field orientation and the comparison between the large scale magnetic field and the smaller scale magnetic field. But what about the energetics? So from the existing observations of the magnetic fields, we can estimate the magnetic field strength. So there is a famous relation called Davis-Chandrasekhar Fermi relation. And this relation has been used until now to estimate the magnetic field strength. So this magnetic field strength is a function of density, which can be extracted from the column density maps. And then sigma VLSR is the velocity dispersion, which can be quantified based on the molecular line observations. And sigma theta is the dispersion in the magnetic fields. So this is the only information we can extract from the dust polarization observations. And rest of the parameters, density and the turbulence information, we can extract from the archival data on column densities and multi-line observations respectively. And this relation has is based on the 2 important assumptions. So one is that the fluctuating magnetic fields is corresponding to the turbulence. So the fluctuating magnetic field strength to the ratio of fluctuating magnetic field strength to the ordered magnetic field strength is proportional to the turbulence level to the magnetic field strength. This is the ratio of sigma v is the velocity dispersion corresponding to the non-thermal velocity contribution, and this is VA is corresponding to the alphonic velocity. And this ratio is essentially can be imprinted into the the magnetic field orientation. So the sigma theta can be can be proportional to the delta b by b0. So how we can understand this? So if we have ordered magnetic field lines, and that means that B0 will be dominating over the fluctuating magnetic field strength. That means that the magnetic fields are very ordered and the dispersion of magnetic fields will be smaller. Sigma theta is this dispersion in magnetic fields will be smaller. And in the other case, if the turbulence is dominating or the fluctuating magnetic field strength will be dominating, and the ordered magnetic field strength will be smaller, that would reflect as a very chaotic or the higher magnetic field orientation. So you can see that there is a huge difference in the dispersion in the magnetic field lines. If the turbulence is dominating, then the sigma theta will be higher. If the magnetic field order magnetic field strength will be higher, then the sigma theta will be smaller. And then based on this assumption and based on these parameters, we can estimate the magnetic field strength. And also based on this, we can estimate the alphonic Mach number, which can actually relate the magnetic fields versus turbulence. And similarly, we can estimate the mass to flux ratio criticality, based on which we can understand the importance of magnetic fields in comparison to the gravity. So these are the important factors based on which we can understand which is the dominating factor. And this table gives the magnetic field strength in two cores, because I'm only concentrating on these two cores because this has less number of vectors, and these two cores are twin cores. They are at the same evolutionary stages, and their mass is similar, and their turbulence level is similar, and but their magnetic field strength is different. Magnetic field orientation is different. But when we look at the energetics, the magnetic field strength for the two cores, the two twin cores, is same, of the order of 40 microgauss. And if you look at the mass to flux ratio, is same, like for two cores is something like 1. That means that mass and the gravity and the magnetic fields are at the equipartition. And if you look at the alphonic Mach number, that is also something like equal to 1. In both the cores, both the magnetic fields and turbulence are similar. And when we compare these three factors in two cores, in twin cores, I can say, all the three factors are in equipartition. But however, why this magnetic field orientation is different? So I state here that all the two protostars are at the same evolutionary stage and have all the energetic at the same equipartition, and why the magnetic field orientation is different in these two cores. So we actually look at the gas velocity in these two cores. So for this, we have used the IRM M2H plus data, and then we try to construct the velocity gradients. So velocity gradient map can be constructed based on the centroid velocity map from the multi-line observations. If we have the centroid velocity map, this can be modeled in terms of constant velocity and the velocity gradient in the alpha in the RA and deck direction. And delta alpha and delta deck is the the separations of the pixels from the central region of the course. And here A and B indicates the velocity gradient in the alpha and deck directions. And if we know this alpha and deck, we can estimate the gradient of velocity and also we can estimate the direction of the gradient. So in this diagram, the black vectors show the gas motion inferred from the velocity gradients, and the red segment are from the magnetic field orientation. You can see that the gas motion in this one core is preferentially perpendicular to the magnetic field orientation, and this we infer as the rotation of the core. And if we can infer the rotational axis, that would be perpendicular to the long axis of the core, and that would actually align with the magnetic field orientation. And you can see here that the motion of the gas is very systematic in one core, but if we look at the gas motions in the another core, you can see there is a kind of converging motion. So one velocity component is coming from the top left corner, and then another velocity component is coming from the bottom right. And this two velocity components, gas motions, are coming and converging with each other. So that could be the reason behind the change in the magnetic field orientation in one core. So we propose that the gas motions, which may be happening from large scale to the onto the main filament, could be altering the magnetic field orientation. So that effect would be minimized in one core, but the gas motions could be dominating in the another core. So in order to continue our efforts, what we did is that we have conducted multi kind of polarimetric observations towards the same region, larger part of this cloud. And you can see that previously there are very few vectors. You can see that the densely populated vectors, which we have recently obtained from aim-pole polarimeter, and also mirror polarimeter in the USA. And the central part is still we cannot probe using these observations. And we want to combine these existing observations already been published and these recent observations to get a comprehensive picture on how the magnetic field orientation can change as a function of column density. You can see that in the low column density regions, the magnetic field orientation is essentially uniform. And when we go into the denser regions, magnetic fields are exhibiting very complex morphology. But we still lack of this magnetic field information in the intermediate density regions. And when we look at the relative orientation of the magnetic fields with respect to the filament, you can see that the dominance of the perpendicular component, like around 80 degrees in the low density regions. So this 90 degrees corresponding to the 90-degree orientation between the filament and the magnetic field orientation. But in the high density regions, the magnetic field orientation is complex. There is no preferred orientation with respect to the filament or the large scale magnetic field lines. So we still lack of the this information in the intermediate densities from 6 to 10 magnitude. So in the another study, so up to here, I was actually discussing about the magnetic field orientation and their role in the very quiescent low mass stuff. I mean filamentary like clouds. But hereafter, I'll be discussing about the importance of magnetic fields in the highly turbulent and higher in these highly turbulent regions such as the H2 regions. So here in this region, I would like to introduce a filament. You can see in the top left panel. So there is a filamentary like molten cloud with uniform density, or the density will be higher in the ridge of the filament or the center of the filament. And suppose there is a dense cloud, and then that would collapse to form the high mass star, and eventually it can actually ionize the surrounding material and then form a bubble like H2 region. So since this H2 region will be embedded within the filament, and then that will be very highly pressurized, and because of that there will be expanding ionizing fronts. So this high density ionized medium can expanding into the low density regions. If we look at the density profile of the filament, there will be high density at the center and then low density in the rest of the filamentary regions. So because of this anisotropic distribution of the material, this expanding ionizing fronts can expand into the low density medium, and then generally, naturally, it can form a bubble-like structure, bipolar bubble-like structures. Okay. But if we have the magnetic field lines, so generally magnetic fields can be aligned perpendicular to the magnetic field lines. So something like this, perpendicular to the magnetic field lines. So this is the filament, and then you introduce the magnetic fields perpendicular to the filaments. So if we have such a configuration, what is the consequences? That is what we want to study. So if you have the magnetic field lines perpendicular to the filament or parallel to the expanding ionizing fronts, so what are the consequences we can see? So since the ionized medium can actually drive the ionizing fronts, and because this medium will be ionized and that actually coupled to the magnetic field lines, since these ionizing fronts and the magnetic fields are parallel to each other, so these ionizing fronts can be the flows can be accelerated. And then if you have a perpendicular configuration, if the ionizing fronts are moving like this and the magnetic fields are like this, then magnetic fields can actually suppress their flows, then can hinder their flows. So we can have these two consequences here. So in the low density regions, magnetic fields, if they are parallel, they can actually aid or support the expanding ionizing fronts. And if you look at this region, you can see that So initially, the diameter or the radius of the H2 region will be smaller, and as with respect to time it expands to the filament, it can actually compresses the filament material and then form the dense clouds. You can see there is a formation of dense clouds, and eventually this dense cloud in the second generation, it can actually trigger collapse and form the second generation of stars. And what happens to the magnetic field lines? Initially, B fields could be weaker because of the ionizing fronts are expanding, and then these expanding ionizing fronts are actually throwing or compressing the cloud material as well as the magnetic field lines. There will be compression, there will be a formation of the dense clumps, and also there is a compression of the magnetic field lines. So initially, the magnetic field pressure will be smaller, but in the later stages, magnetic field pressure will be highly dominating. And once the magnetic fields have become stronger, they can drive many physical processes. One could be that the magnetic fields can actually help in throwing or in escaping of the expanding ionizing fronts, or in the stabilizing the modular clouds, dense clumps from a gravitational collapse. So here is the picture. You can see that. So these are the dense clumps, as I was showing. So these are the dense clumps are formed in the vicinity of the H2 region or the bipolar H2 region. So this red background is corresponding to the dust emission, which are very cold, like 10 to 20 Kelvin. So the red contours or red color red background is the dense massive cores, and they are very cold. And here the gray contours are corresponding to the H2 region. Here I shown with the red or orange color. You can see here the yellow contours are corresponding to the H2 region, and the red contours are corresponding to the dust cold one. So there is an interaction between the hot ionized medium, as shown with the yellow gray contours, and the cold component, as shown with the red contours. You can see that there is a change in the curvature of the ionized medium. So these gray contours are nothing but the ionized medium. You can see that all of a sudden their orientation is they're freely expanding here. So you see the separation between each contour in the mid plane. But as soon as you can see their distribution close to the dense cores, they are compressed. You can see the separation between the contours, they are compressed. And also you can see the curvature, they are bent. You can see there is bent. So there is an interaction between the dense cores and then expanding ionizing fronts in this region. And this is the region where the magnetic fields also get compressed. You can see that the magnetic field orientation, as shown with the yellow segments, they also following the, this curvature, this compression. So you can see that their compression, their orientation actually configured into bow-like structure. You can see that this curvature is more in this one because there is a more interaction of the H2 region. And in the another core, in the right dense core, you can see that the both compression is different and the curvature is also is not that much. Less curvature or less compression.
Eswaraiah, yes. five more minutes.
Yeah, I'm going to summarize that. So here actually what we did is that we try to estimate various energetics, magnetic field pressure, turbulence pressure in the dense cores, and the external pressure from the H2 region, which is known as the thermal pressure. Then when we compare all these energetic parameters, what we found is that in clump 1, the clump 1 pressure, which is driven mainly by the magnetic fields and turbulence, and then gas thermal pressure is dominating over the feedback pressure. So once the clump pressure is dominating, then this clump cannot move. It can actually obstruct the ionizing fronts, and then it can also guide the ionizing expanding fronts. So in the another core, both the clump internal pressure and the feedback pressure are actually equal. And what I want to say here is that even we have the contribution from turbulence and magnetic field lines, and because of the dominance of the stellar feedback in this clump, so you can see that there's more curvature actually being observed in this one. That means that the stellar feedback is dominating, and that is actually what triggering the second generation of star formation. You can see that the different symbols are corresponding to the stellar population. You can see that more number of interstellar objects can be found in this one in comparison to the another core. And we have earlier done the near-infrared polarization observations and traced the magnetic field orientation towards the similar region, bipolar H2 region. You can see that red background is correspond to the cold medium, and this another green is correspond to the hot medium. You can see that the larger scale magnetic field orientation is taken away along the bipolar bubbles as shown with these contours. Okay, and you can see that the formation of dense cores in the vicinity of the H2 region here. So unfortunately, based on the near-infrared polarimetry, we cannot trace the magnetic field orientation in the dense cores, but we can trace the magnetic field orientation in the low density regions. We can study their role. What we propose is that initially the magnetic fields could be important in the formation of filament by channelizing the material flows along the magnetic field lines as shown in this panel. And then later, once the formation of its region, and consequently there is a expanding ionizing fronts, this magnetic fields could have guided this expanding ionizing fronts to form the spectacular bipolar like bubble like structure. And recently, we have probed the magnetic field orientation in the ring-like bubble, and there are formation of several clumps. In one clump, there is a kind of massive star formation actually going to happen, or is already been happening. And magnetic field, you can see that if there is a completely compression of the magnetic field lines, we could see that we could see only the parallel magnetic field orientation. Okay, if you have the expanding ionizing fronts, they can actually align the magnetic field lines perpendicular to the expanding ionizing fronts. But to our surprise, we could probe both, perpendicular and parallel components. So this work is under progress. And similarly, we are studying to understand the role of magnetic fields in the massive star formation. The left panel shows the magnetic field orientation in the large scales. Essentially, they are very ordered, as shown with the red and then yellow segments, and they are perpendicular to the nearly perpendicular to the elongation of the clump. But when we look at the magnetic field orientation at the smaller scales, you can see there are very random, not very random, but they are ordered. But you can see multiple component of magnetic fields. They are pointing towards the dense regions where the massive star formation actually happening. So this work is under progress. And we have recently also done the H1 narrow self-absorption. This is the absorption line of H1 spectra. So based on the G1 observations, so if you have a H1 spectra and if you have a cold component in the molecular cloud, and that can actually absorb the abundant H1 emission in the background, so that would actually create a narrow self-absorption. You can see the velocity. So the velocity dispersion will be something like less than 1 kilometer. That's why we known as the narrow self-absorption. And when we subtract this narrow self-absorption component from the uniform background component, you can actually look like this. Okay, so even though it should be negative, I shown it as a positive component. So if you have a magnetic field in the cloud, that would actually split the H1 spectra. And based on this analysis, we can actually estimate the magnetic field strength within the molecular cloud. This is the direct observations. These kind of observations are actually very rare. So until now, I was actually studying, discussing about the dust emission polarizations and indirect way of estimating the magnetic field strength. But human experiment can actually help us to estimate the magnetic field strength directly. So this is the summary. So we have studied the magnetic fields in the quiescent environments and also in the turbulent regions. And in one of the study, which has been recently published in ApJL letters, so despite of important role played by the magnetic fields at larger scales, they can be decoupled at smaller scales due to complex kinematics that may arise due to gas accretion flows onto the main filament. And in the another study, we found that massive clumps around H2 regions are the potential sites to investigate the interplay among the magnetic field turbulence and stellar feedback. Yeah, I stop it here, and I will be happy to take questions. Yeah, thank you.
Okay. Thank you, Dr. Chakali, for a very nice presentation. Now we have time for some question, comments. feedback. So I request from audience to either raise the hand and I will call the name, or maybe directly unmute themselves and ask the questions. Please go ahead. Yeah, Neelam, please go ahead.
Yeah, thanks, Eswar, for a nice talk.
Yeah, thanks, Neelam.
Yeah, so actually, when we were showing the region S201,
yeah,
so if you, I can see that some of the, like at the head of this, this is a cometry globule, or
yeah, yes, we can see it as a cometry globule because we cannot see it as a face on view because there is a projection effect. Maybe this is pointing towards us. So yeah, it may be kind of cometry globule. But we cannot say confirmly.
yeah, because if you see at the head, the like the vector, its direction is a little bit different as we go away from the head.
That's true. Yeah, right. So this trend has.
So is there any, means there is a evolution of the magnetic field? I mean, as the cloud evolve, there is change in magnetic field lines? Or?
Yes, definitely, Neelam. So if we can look and observe maybe the H2 regions, which are very early stage. So essentially, the mantle fields could exhibit something like parallel configuration to the clumps. So, but since the massive star formation is very rapid, but such kind of I think observations are not easy to perform. But I think there is an evolutionary stage. Yes.
Okay, thank you.
Okay. Any other question? If not, so yeah, Suvendu, go ahead.
If I may ask, so Ishwar,
Hi, Suvendu.
Yeah. So if you are in the Bistro program, you get access to the data if you are here, or you have to be in Korea or Taiwan or any other institutes to get the data access.
Yeah, we should generally be in East Asian countries, so like or UK, Ireland, Canada.
Okay.
But even Thailand has the access to the Bistro observations. But through collaborations, I think we can get the data.
Okay.
But I think I was about to tell that one of my dreams is to have the India name in this consortium. Yeah.
Okay. Thanks.
Okay. So if there are no further questions, so let's thank the speaker once again. Thank you, Dr. Chakali, for joining and giving a very nice presentation of your research work.
Yeah.
Okay, and I thank everyone for joining today. And goodbye, everyone. Have a nice evening, and then we will see you next week. Bye-bye. Okay.
Thank you.
Bye.
Thank you all. Yeah.